So I realize that these lectures are slightly different from the norm in as much as they are fairly technical, but I hope you appreciate that the ideas that they contain are really fascinating and worth devoting a little bit of time to, and trying to get to the technical aspects of them is not a bad thing. I guess I need to put this onto the slideshow. Oh dear, I've gone to the stop. I think that's where we were. Oh, don't want to do that. This time. And I realize from a couple of the questions that I had that what appears on the transparency is slightly misleading. At the point where I was deriving this continuity equation, I said this implies that. What I should have written down was an equal sign, equals 0 on the left-hand side, because all I'm doing is taking phi star times the Schrodinger equation, which itself is equal to 0, minus phi times the Schrodinger equation, which itself is equal to 0. So this is trivially equal to 0. It's just a reformulation of the Schrodinger equation in a way that manifests the underlying physics. So there was nothing special about doing this. This is a derived result from the Schrodinger equation, and you immediately get to the idea that you have a probability density phi squared. And then I got to the point where doing the same thing for the Klein-Gordon equation leads to this rather worrying result that you have negative probability. And anticipating the solution, I pointed the Pauli and Weisskopf with a reinterpretation, interpreted this as an electromagnetic charge density rather than a probability density, and that can be negative as well as positive. So that will be the way out. So, starting again with the Klein-Gordon equation, very often this is written in relativistic notation, and although it won't be so important for my lectures, it's useful to see what the notation is, because subsequent lecturers may assume that. And the form written up here can be written in a neater form with a 4 covariant and contravariant derivative in this manner. So just to introduce these ideas, in writing down relativistic theories, it's very useful to use 4-vector notation. We met the 4-vector notation for x mu with c, t, and x. P mu, it's e over c and the 3-vector p. So quite generally, you have contravariant 4 vectors with upper indices and covariant vectors with lower indices. And because the metric g mu mu has -1 in the space dimensions, and going from the upper to the lower, you contract with the g mu nu, you bring in a minus sign for that. So that's the operation that gets you between these two. A mu is g mu mu, a nu. And then the A dot B, which I had in writing down my plane wave solution, is to be interpreted as the contraction between a covariant and a contravariant, A mu, B mu, which is A naught, B naught minus A dot B. So the 4 vectors I've already talked about, the momentum and position. We also introduce derivative 4 vectors, which are slightly different in as much as for the contravariant, there's a minus sign associated with the derivative, and the covariant is plus sign. And then in going from the classical equation of motion, where it's described in terms of momentum, you go from the 4 momentum p mu to I h bar d mu. Putting that into the scalar product, the 4 scalar product, p mu, that becomes e squared minus p squared. And that was where I got the form for the Klein-Gordon equation d mu plus m squared equals phi equals 0. So that's just notation, but it's important and useful notation. Now, what I've got with the Klein-Gordon equation is a non-interacting scalar particle. It's just got a term which involves the mass, but there are no interactions. And I would like to study an interacting field. That, after all, is what we study when we do collisions in the laboratory. They're interacting by, for example, the electromagnetic interaction, or perhaps by the weak or the strong interactions. How do we introduce interactions? Well, classically, you will be familiar with the sort of principle of minimal substitution, where you take a momentum and replace it by the momentum plus the charge times the electromagnetic field. So I'm talking about motion of a charge in electromagnetic potential, and this is a 4 potential. It's got the normal scalar potential, which I call A naught, and the vector potential A, and they're put into a 4 vector A mu. So this is a classical rule for introducing interaction with electromagnetic field. Quantum mechanically, we replace P mu by I d mu, and the replacement then that gives you the interaction with the electromagnetic potential is just copying above. You go to I d mu plus E A mu. And now it's very simple to put that in here. I substitute for d mu in here using this substitution. I end up with a new version of the Klein-Gordon equation, which has still got the d mu plus m squared, and everything new I've put onto the right-hand side, and I've called it an overall V. And if you just expand that, you'll find that the V has pieces in which you take an A mu from the d mu and a d mu from the other part to get a linear term, minus IE d mu A mu plus A mu d mu. Or you could take, in both of these d's, the second part, and that gives you the E squared A squared. So this now will tell you about the motion of a scalar field described by phi in an electromagnetic potential described by this 4 vector A mu. And at this point, the smallness of the electromagnetic coupling, which is characterized by alpha electromagnetic, E squared over 4 pi, which is approximately equal to 1 over 137, means that it's sensible and useful to make what's called a perturbation expansion of V in powers of alpha. Oops. No, I'm in trouble. Let's go page up. Now, we don't see alpha here, but we see E. E is a component of alpha, so it's effectively powers of E. So the leading term in V would be this linear term in E, and then this will be a next order term. So for the first iteration of this, I'm just going to approximate V by the first term. And now we're at a stage where I can address an interesting question. In the first lecture, I stressed that forces were due to the exchange of particles, and that the important aspect in calculating this was to work out the propagator. In this case, it would be the propagator of the virtual photon exchanged between the electron and the nucleus. But now I've got my scalar field interacting with the electromagnetic field, I should be able to draw something similar. So let's see what we can draw. The dotted line refers to the Klein-Gordon field phi. It has an interaction through that V term with the electromagnetic field, which is this red curved line. That's the photon. So I can draw a diagram like this in which I exchange a pi between the upper and lower vertex. And this object here, a virtual pion, will have a propagator. And so the first exercise is to calculate for the Klein-Gordon equation the propagator of the pion. And that will teach us whether some of the ideas that I've been stressing about the importance of including antiparticles and the Pauli-Weisskopf interpretation, whether these are right, and we'll see that as we go along. This will be the pion propagator. So let's see how we calculate the pion propagator. We want to solve this equation. I've changed phi to psi for no good reason. I'm sorry for that, but they're basically the same thing. Sometimes I use phi for the non-interacting case and psi for the interacting case. So let's take this structure. And this is the Klein-Gordon equation with interactions where we know the form of V. And we want to solve it. So it's a well-defined problem. How do we solve it? Well, there's a very elegant way of solving this that you may or may not have seen before. My statement is that you can write a solution to this equation in the form that psi is given by phi, and now I am using the notation where phi will be the solution to the non-interacting Klein-Gordon equation. Psi is the solution to the interacting Klein-Gordon equation. Psi can be written in terms of phi minus an integral over space-time, x primed, a function that I call delta f that will turn out to be the propagator, times this v, which depends upon x primed. It depends on the position that the interaction occurs, and psi of x primed. So that's just a statement. I now have to justify it. So let me first of all make these definitions a little bit more precise. Phi satisfies this three-particle Klein-Gordon equation. I've already found a solution for phi. It was that plane wave state that I wrote down, e to the I minus ip dot x. So I know phi. I know its functional form. What is this function delta f? It's given the name the Feynman propagator. And I tell you that this is a solution provided delta f satisfies this equation, which says that del squared plus m squared acting on this Feynman propagator is going to be a four-dimensional delta function. Remember, although it's not exhibited clearly, that this derivative acts upon x, the x index. So this derivative is acting on that index, and this delta x primed is the one that's being integrated over. The four-dimensional delta function, it's a four-dimensional Dirac delta function, and it has the following property. Take any function fx primed, integrate over space-time with this delta function, delta 4 x prime minus x, and the answer is f of x. You can make a mathematically sensible definition of this delta function using distributions, but for the purposes of studying the physics, this is my definition of my delta prime, because it will always appear under integrals when I'm calculating physical properties. And now it should be possible to see how this equation in the red box is a solution to the equation at the top that we wanted to solve. Let's apply to this equation del squared plus m squared to both the left-hand side and to the right-hand side. So del squared plus m squared on psi should equal minus v psi, but what it actually equals is del squared plus m squared acting on phi, but that's 0, so I can just drop it, minus del squared plus m squared acting on this integral. The del only acts on the x part, so the only term in here that depends upon x is the Feynman propagator. So I get a del squared plus m squared acting on delta f, and I use this to substitute for delta f delta 4 of x prime minus x. That stress, what I'm doing is I'm applying del squared plus m squared to the right-hand side. So now finally, I have to do an integral d4 x prime, delta 4 of x prime minus x, v of x prime, psi of x primed. But here is how you do that integral. What ends up is you get v times psi with this minus sign. So rather trivially, I have a solution to this equation in terms of the Feynman propagator. So you might say, well, that looks a bit too simple, and of course it is too simple, because until I tell you what this Feynman propagator is, I haven't solved anything. But it has formulated it in a way that I can concentrate on solving this equation. So that's where the work goes into solving for the propagator. And it's actually not too hard to solve for this propagator. What we have is an equation in configuration space, x and t, x, y, z, and t, but I can solve it more simply if I go to momentum space. So to do that, I take a Fourier transform of both sides. So I'm taking the Fourier transform of the left-hand side, which involves an integral d for x prime minus x, e to the minus ip x prime minus x, and p is a conjugate variable to x prime minus x. So this is my momentum variable. And I do exactly the same on the right-hand side. I've got integral d for x prime minus x times the delta function times e to the minus ip x prime minus x. And now I do those integrals. The right-hand side is easy because I know how to do an integral over a four-dimensional delta function. It just gives me e to the ip. I set x primed equal to x. So it's e to the ip times 0, which is just 1. So this integral is just a factor 1. The left-hand side is also pretty easy once I recognize that I can do this integral by effectively operating with the derivatives on the exponential. You can write it as a surface integral plus the terms where this acts on the exponential. So I get a d mu acting on e to the minus ip dot x prime minus x. This d mu acts on the x, so you bring down a p mu. This gives you another p mu. You end up with a minus p squared from that. So the final answer you get is minus p squared plus m squared acting on delta f. Well, once I've got this to be p squared plus m minus p squared plus m squared, I can take it outside the integral. I'm left with an integral e to the minus ip dot x prime minus x delta f x prime minus x d4 x prime minus x, which is just the Fourier transform of the original Feynman propagator. So this is delta f in momentum space. And the factors all work out in the way that's shown here. This form I can instantly solve. It tells me that this Fourier transform, I put a prime on it now to distinguish it from the non-transformed one, is 1 over 2 pi squared, 1 over minus p squared plus m squared plus I epsilon. And if you can remember my introduction in the first lecture, you'll begin to recognize the form of the propagator, which I had as 1 over k squared. Here it is p minus p squared plus m squared. So this is actually for a massive field. This m sitting here is the mass of the Klein-Gordon field. So it's the form, actually, that one gets for the W boson propagator rather than for the electromagnetic one. I stress it's not the W boson propagator because this is a scalar field, but it has the same structure. So you begin to see how the form of the propagator can be derived from the underlying quantum mechanical equation, which was the goal of the exercise. And if I want to get the Feynman propagator in configuration space, then I just do the inverse Fourier transform to get back to that result. So this is my derivation of the pion propagator. And it contains a lot of information. I've now actually solved the original equation, because now that I have a functional form for delta f of x prime minus x, my solution to the equation just involves an integral. It's not quite that simple, as you'll see in a moment, but in principle, I should be able to do that. Well, not quite, because you'll notice that the solution that I'm looking for, psi, appears under the integral, so it appears both on the left-hand side and right-hand side. So that's a complication. But we're getting there. Let's tackle that complication. Here is the structure of my solution written out again. Psi appears left-hand side and right-hand side. What do you do about that? Well, under the integral is this v. V, if you remember, involved the electromagnetic field, and it involved the coupling E. So if E is small, I can solve this equation iteratively in powers of V. And 2 powers of V will be smaller than 1 power of V. So this would be a useful way of proceeding. How can I do this? Well, what I can do is I can take this solution for psi and substitute it into what appears on the right-hand side. So the first term in here, which doesn't involve V, will be phi. So I can put phi in here as the first term, and then there'll be a second term coming here, which involves V. So here's the first term, psi equals phi of x. Not very interesting, because that says that the solution to the interacting case is approximately the solution to the non-interacting case. It's true if the interaction is small, but it's not very illuminating. It corresponds to saying that if I have a potential of finite extent, my particle essentially misses it. It goes through unperturbed. Now I work a little bit harder, and I substitute this into the right-hand side to get my next approximation to the solution. It's written in green here. This I can actually compute because it's an integral over d4x, delta fx prime minus x. I had an explicit form for that in terms of my propagator. V of x primed I know, phi of x primed, well, phi of x is the free particle solution. It's my e to the minus ip dot x. So I know how to do this. What's the interpretation of that? Well, you can interpret this as the particle coming in, interacting with the potential at the point x primed, and then going out, the observer is observing these particles at the point x. And in going from the point x prime to x, we have a propagator. So we interpret this as a propagation from the point at which it interacts to the point at which I see it, is the Feynman propagator. It's linear in x. I integrate over d4 x primed if I've got a potential of finite extent. This is an electromagnetic potential of finite extent. I integrate over this volume. So I consider the possibility that it interacts anywhere in this volume to get the full answer. And then I do this again. I substitute I look at the next term in substituting for psi, which effectively takes this piece and puts it in there. And I find I now have my integral d4, well, I've renamed this x primed, x double primed. I'm substituting what I found in here, and you can see that I'm putting that up here. So what I end up with is 2 propagators, one propagator from here and one propagator from substituting in here with this green term. Here's my 2 propagators. I've got one insertion of the potential from the top and one insertion from putting this into the right-hand side. So I've got 2 interactions with the potential. And if V is small, this term will be small relative to the leading term, and this will be yet smaller. And the interpretation is that my particle interacts twice with the potential before going to the observer. And this way I build up an infinite series, a perturbation series. It's called the Born series. And the beauty of this is you tell me how accurately you'd like this calculated, and I'll just continue working until I get to that accuracy, provided V is small. So it works for electromagnetism, where alpha electromagnetic is 1 over 137. It converges very quickly. It doesn't work so well for the strong interactions. If the perturbation is of order 1, you'd have to keep an infinite number of terms, and this is the problem in solving the strong interactions. That means that this perturbation expansion doesn't work. However, in many places that we're able to probe, for example, even with the strong interactions, provided we probe at very large momentum transfers or large energies, the strong interactions themselves become perturbative, and we can use these perturbative solutions. So very much in what you hear about the study of the standard model, the justification for the results will be based on perturbation expansion of this type. Okay, where do we go from there? we're left with a problem. The problem is that the energy eigenvalues can still be positive and negative. I've got an equation. I can't just impose Pauli-Weisskopf interpretation. I've got an equation. That equation has to tell me what the solution is. So now let me go through the discussion to see if Pauli-Weisskopf interpretation falls out of this. This is helped by the observation of Feynman and Stuckelberg, which very loosely is presented in this graph here, where if I've got a positive energy solution to my Klein-Gordon, which I'm now going to call pi plus because I've introduced an interaction with the electromagnetic field. It's a charged field I'm studying. So I have a pi plus, and I'm plotting its evolution in time. Time goes upwards. It's got a positive energy, so it's a well-interpreted state. And the wave function evolves by the usual phase factor, e to the minus I e t. Now, rather trivially, I can put e to the minus I e t as minus e times minus t. And at first sight, that looks just too simplistic to make any sense, maybe even at second sight. But if I was to try and interpret this as a negative energy solution, I would have to say it's moving backwards in time. And what Feynman and Stuckelberg suggest is that a positive energy solution of a pi plus moving forward in time is equivalent to a negative energy solution of a pi minus moving backwards in time. If you think about the charge flow, you have to go from positive to negative in order to have the same interpretation, because one is moving forward in time, carrying the charge forward in time. The other is moving the charge backwards in time, but if it's a negative charge, it's having the same net effect of the transfer of the charge. So the Feynman-Stuckelberg interpretation is that you can reinterpret, effectively one will want to go the other way, a negative energy state moving backwards in time as a positive energy antiparticle state moving forwards in time. Now, consider a pi plus interacting with our electromagnetic field. So the pi plus comes in at time t1, it interacts in the potential, then interacts at time t2 again with the potential and comes out. And the final state and the initial state are the bits beyond the extent of the potential. But given that the interaction can occur anywhere here in the timeline, I have another possibility, which is the same incoming state interacts at time t2, and then at an earlier time t1, a state is emitted. This would require my state going backwards in time, which is why I started to think about that possibility using the Feynman-Stuckelberg interpretation. The interesting thing about this is, if you think about what's happening at intermediate times, so we start off at a time less than t1 and cut this diagram, and there's only a single line there. That means that we have the same incoming pi plus in both cases. Similarly, at times greater than t2, you cut it, you've got one outgoing state, the same pi plus going out. So both of these are contributing to the same physical process. But if you interpret what happens between time t1 and t2, there's a difference. Here I only cut one state. Pi plus is going to an intermediate pi plus is going to an outgoing pi plus. On this side, on the other hand, there are three states I have to cut, which would correspond to a forward-going pi plus, forward-going in time. Then we've got a backward-going state, which I'm going to interpret as a backward-going pi minus, and then a forward-going pi plus. Oops. What happened there? So here's my pi plus. It's going backwards in time here, but I'm going to reinterpret this as a forward-going pi minus by this reinterpretation. And then here's my forward-going pi plus. So I can make sense of the physical interpretation of this, pi plus going to pi plus going to pi plus. Here it's pi plus going to pi plus, pi minus pi plus going to pi plus. What's happened here is that you've pair produced a pi minus and a pi plus. If you've got sufficient energy in this process, there's nothing that prevents you pair creating out of the vacuum, as it were, with the energy of the interaction process. So relativity says that such processes should occur. And my interpretation using Feynman-Stuckelberg of these diagrams is that this is the extra diagram that's generating that. So far, I haven't made connection with the underlying Klein-Gordon equation, but I'm going to try and do that in a moment. If this is a correct interpretation, the structure we got from solving the Klein-Gordon equation in an interacting electromagnetic field should contain this information. Does it? So let's see. The discussion I gave you about interpreting the perturbation expansion is that the propagator is responsible for taking you from the point of one interaction to the point of the second interaction, or to the point it's observed. So this Feynman propagator should contain the information that says that there are two ways I can get from here to here, one with an intermediate pi plus, and one which requires a pi plus, pi minus, pi plus. Here is the form of the propagator that we derived. It's written in terms of an integral over the momentum, so this is the x-space solution. Here was the propagator we derived in momentum space. And it's the Feynman, it's the Fourier transform of that. Now, actually, you have to do a little bit of work here. You have to do the integral over the time part of this. This is d4p, so this is dt, and then the dx, dy, dz. So I'm going to do the dt integral. If I do the dt integral, this is what I end up with. Deriving this result is not that difficult. It's particularly not that difficult if you're familiar with contour integration. I have a few minutes to go over the next slide a little bit, but I am aware that many of you will not be familiar with contour integration. So the next slide is just to be treated for those that have seen how to do contour integration. It's as a simple way of deriving the final result in red from the result in blue. If you haven't seen it before, then you might be motivated to look up Cauchy's theorem to figure out how it works. But I'll only go through this briefly. This is one of the transparencies I put in that you can look at leisure. So the next slide deals with how you derive the form in red. It's kind of interesting how it works. This is what I'm trying to integrate, and I want to do the dp naught. Looking at the denominator, p squared plus m squared, p squared minus m squared, I've done something very important, but I slipped it in without commenting before. I have realized that if I integrate d4p, there's a place where p squared equals m squared. And that gives me a real problem. It's a divergence. But I've been tempted to regulate that divergence by going into the complex plane, adding a small complex part, I epsilon, where epsilon is a small number. And what I'm going to say is that provided when I finally calculate my process using this propagator, if I can take epsilon to 0 and it's well behaved, this will just be a convenience in regulating intermediate infinities. And that's the way that we are forced to proceed when looking at field theory calculations. I'm skipping over it a bit, but it's important that you know that you have to do this regularization structure. So I'm telling you that's what I'm going to try and do, regulate by moving the pole into the complex plane. If I look at the zeros of this, p squared plus m squared minus I epsilon, they occur for p naught squared. It's p squared plus m squared minus I epsilon, or p naught is plus or minus the square root of p squared plus m squared plus minus a small imaginary part where delta is proportional to epsilon. So effectively what this means is when I do the p naught integral, there's no point at which the denominator vanishes because the p naught is along the real axis. The integral is along the real axis. And now my Feynman propagator has the structure that it's got two places where it vanishes. So it's P naught minus omega P minus I delta and P naught minus omega P plus I delta. And this is where Cauchy's theorem allows you to do the integral rather straightforwardly. What you do is, although this integral extends along the real axis, you close it by either closing along a large semicircle in the imaginary plane above or below. You choose the point such that if I'm moving into P naught imaginary, then this exponential can become a negative exponential, e to the minus the modulus of P naught times the modulus of T prime minus T. And that will mean that the contribution that I'm adding is essentially zero. That's the trick in doing this. So you convert this into a contour integral, and then you use Cauchy's theorem to pull up the residue at the poles. As I say, if this is unfamiliar to you, it won't be familiar to you as a result of what I'm saying, but it points you in the direction of looking up Cauchy's theorem and going back to this slide. Now, there are two poles in here. If T prime minus T is greater than 0, then I have to close in the lower half point. I have to take P naught to be minus IPI, because if I do that with T prime minus T greater than 0, this exponential will become e to the minus something real and will be small as I want it to be. So for this choice of ordering of T prime and T, I have to close the contour in the lower half. If T prime minus T is less than 0, I have to close it in the upper half. And that means you get two pieces, one which picks up the residue of one pole and has the form e to the minus I omega p T prime minus T, and the other one which is e to the plus I omega prime T prime minus T. So that was a long diversion to justify that I get a structure like this in which I have to worry about whether T prime minus T is positive or negative. And putting that together now, I can make the final interpretation that I wanted to. Here is my propagator. Here is the result that I had in red before. And I can write this as two pieces. One part in which T prime minus T is positive, and then I get the e to the minus I omega p dot x, e to the minus I omega p dot x, f plus at x primed, f plus star at x. That corresponds to the part where T prime minus T is positive, but there is a second part where T prime minus T is negative, and for that I have to use the opposite sign of e to the ip dot x, which is going to be the f minus of p. So the whole importance of this discussion was that theory has forced us to a definite structure for the Feynman propagator. That structure forces you to have two components to it. One in which you've got f plus, which corresponds to the usual e to the minus iet, the positive energy solution. That corresponds to this propagation in here. But we're forced also to have an f minus, which has the wrong sign, e to the plus iet, and that would correspond to a negative energy solution, or a positive energy solution moving backwards in time. And that's what's giving you this part of the propagator. So indeed, the interpretation I was presenting to you here falls out from a detailed study of the structure of the propagator, which was a central part to the solution to the Klein-Gordon equation. Now, I realize that this has been a fairly technical discussion, but I hope at least you've grasped from this the fact that by going to the relativistic form of quantum mechanics, we have encountered some problems, but by solving the problem carefully, we have encountered a solution which is made, you can get a physical interpretation using the ideas of Pauli and Weisskopf, but which are actually present in the original equations. It's not a postulate, it follows from the equations. So the positive and negative energy solutions are needed in order to make sense of these two different possibilities for how you go from pi plus to pi plus. And now you can actually see why it wouldn't be correct to treat the negative energy solutions as unphysical. Because had I done that, I would never have got this as a contributing part of the process going from A to B. I would only have had this piece. And once I got to an energy at which the pair production was possible, my answer would have been wrong. So it's absolutely physically crucial that you have these additional contributions. And indeed, when I come to look again at the causality discussion, the reason causality was failing in quantum mechanics was that I was missing these additional contributions to the propagation from point A to point B. And these contributions serve to cancel the piece that we got when we went out of the causally connected domain. So there's my propagator for the plus, there's my propagator for the minus. So that's all I wanted to say today. Just to close, let me say that if you're interested in reading more about the subject, the reference most close to the presentation I'm given will be found in Hartstein and Martin, Quarks and Leptons. There's another nice introductory treatment of propagators and gauge theories in particle physics by Aitchison and Hay. And modern courses often go to Peskin and Schroeder. That's certainly only for the experts. So some of you I know are already experts and probably are familiar with Peskin and Schroeder. But I'll stop there. Thank you.
We'll begin the discussion session in a few minutes.